Thank you, Ingrid. Um, so this is just to let you all know, this training was originally scheduled to be an in-person training in West Lafayette, Indiana, and we didn't get a great deal of in-person attendance, so it was then going to be hybrid, and eventually we just turned it into a virtual training, and that's why the format is as it is. Normally, we would have split this up into two two consecutive days, 2.5 hour trainings each. So format's going to be a little different, but hopefully it all works out for everybody. All right. And this is a basic drinking water math course. It starts out very basic, and we will get into a little bit more advanced concepts towards the end of the day. So the Great Lakes Environmental Infrastructure Center is an environmental finance center. We're part of the Environmental Finance Center network. We concentrate our efforts on training and technical assistance for small water and wastewater systems in EPA Region 5. And we are located up here in the Keweenaw Peninsula of the Upper Peninsula of Michigan. So what are we going to talk about today? We're going to talk about some basic math. We'll talk about conversions. We'll discuss area, volumes, flows, detention time and loading. We'll talk about head and pressure. We'll get into some dosages and some chemical feed rate information, specifically with chlorine. And we'll have plenty of opportunities for working problems. So let's get into it. Like I said, we're starting off basic. We're talking about fractions, and the idea of a fraction is it's part of a whole. The top number or the numerator is how many of those things you have, and the bottom number or the denominator is of how many total there were there in the first place. So in this instance, there are 3 pieces of pie taken out of the 8 pieces of pie. So we would have 3 in the numerator, 8 in the denominator. So that's 3/8 of that. So we take these fractions and how do we convert them into numbers or into percentages, and we're going to divide the numerator or the top number by the denominator, the bottom number. And in this case, we divide 3 by 8, we get 0.375. So that's we have a decimal there. The 3 is in the 10th place, the 7's in the 100th place, and the 5 is in the 1000th place. If we want to look at that as a percentage, we're going to take and because a percentage is the number of parts per 100 parts, we're going to convert that decimal to a percent by multiplying by 100. And if we do so, we get 37.5%. So 37.5% of that pie was taken. All right. The next concept we're going to talk about is multiplying and dividing fractions. It's odd in that this is an instance where multiplying and dividing is actually easier than it is to add and subtract when you're dealing with fractions. So when you multiply numbers, you're going to multiply the 2 numerators, the 2 top numbers together, and you're going to multiply the 2 bottom numbers together, and that's going to give you your answer. So we have an example of 3/8 multiplied by 4/5. And when we do that, we multiply the 3 by the 4, and that gives us 12. We multiply the 8 by the 5, and that gives us 40. We can simplify that. We can figure out what number goes into both the 12 and the 40. What's the largest number that goes into both of those? And in this case, it would be 4. So if we divide both of them by 4, the 12 and the 40, that gives us 3/10. So 3/8 multiplied by 4/5 is equal to 12/40, but it's also equal to 3/10. Now to divide fractions, we're going to use the keep, change, and flip method. So we're going to keep the first fraction, and we're going to change the division sign to multiplication, and then we're going to flip the second number. So if we have 3/10 divided by 4/5, we're going to keep the 3/10. We're going to change the division to multiplication, and we're going to flip the 4/5 upside down and make 5/4. So when you do that, we end up with 15/40, because once again, when we multiply, we're multiplying the top or the numerator, and then we're multiplying the bottom or the denominator together. When we do that, it's 3 times 5 is 15, 10 times 4 is 40, 15/40. Once again, we can reduce that down, we can simplify it. In this case, we divide by 5, which is the greatest common factor between 15 and 40. If we divide 15 by 5, we get 3. We divide 40 by 5, and we get 8. So our answer is 3/8. So if we take 3/10, we divide it by 4/5, we end up with 3/8. Now, next we're going to look at adding and subtracting fractions. And as I said, adding and subtracting is a little more difficult than multiplying and dividing in this case. So if we've got 3/8 and we want to add that to 4/5, the thing we want to do is we want to make sure that the denominators of the bottom number are the same. That's going to make it easiest for us to add them together. So we want to find a number that's as low as possible, but both 8 and 5 go into it. In this case, we're going to just multiply those two numbers together. 8 times 5 is 40. So we're going to make our 3/8 and our 4/5 into something over 40. So we do that. If we multiply 8 by 5, that'll give us 40. And we multiply the 5 by 8, that gives us 40. So the 3/8, we're going to multiply top and bottom by 5. And then the 4/5, we're going to multiply the top and the bottom by 8. If we do that, it gives us 15/40. That 3/8 becomes 15/40, and the 4/5 becomes 32/40. So we add those two together, and we get 47/40. So we can make that a little simpler. We can if we take 40/40 out of that, which would be equal to 1, we end up with 1 7/40. So that's adding fractions together. Now, we'll change gears a little bit and we'll talk about the basic principle of algebra. So it's the idea that if we do the same thing to two different sides of an equation, we will get it doesn't affect the equation. So if we multiply both sides by the same number, say same conversion factor, it doesn't change the equation. It's like multiplying both by 1. So we can so we look at an example, and we had an employee that read 160 water meters during their 8-hour shift. And we want to know how many meters the employee can read per hour. So when we do this, we write the equation, the problem where y is equal to the number of meters per hour, and we take our 8 hours times y, and that's equal to 160. We could also write that as 8y equals 160. We get rid of the hours and the meters to simplify this. But to solve, we're going to divide both sides of the equation by 8 hours. So if we do this, we look at it, divide both sides. So if we had our 8 hours times y over equal to 160, we divide both by 8 hours. We get 160 meters divided by 8 hours, and that gives us our hours are going to cancel, and we're going to get y on one side of the equation, and we'll get 160 meters divided by 8 hours on the other side of the equation. So our y is equal to 20. When we divide the 160 by 8, we get 20 meters per hour. So that individual is able to, on average, read 20 meters per hour. So we're going to look at using doing math problems using conversion factors. So this will be something that's really important, something that we'll do multiple times throughout this. It's an important thing in doing water math. We've got a tank and it holds 100 cubic feet of water. We might want to know how many gallons that is. All right. So we're going to take our 100 cubic feet and we're going to multiply that by a conversion factor. So there's, in every cubic feet of water, there's 7.48 gallons. Okay, so that's 7.48 gallons divided by 1 cubic foot is equivalent to like 1. So we're just multiplying it by really 1. And what happens is when we multiply those together, our cubic feet are going to cancel out. So the cubic feet on it would be 100 times 7.48, and that'll give us 748. The cubic feet cancel out, and we're just left with units of gallons. And we'll see this several times when we go through doing problems. So that's how we go. We use a conversion factor and we go from cubic feet to gallons. We could go the other direction if we like. And the reason we can do that is that a cubic foot over a cubic foot is equal to 1. They cancel each other out. And we're going to get more into this cross-canceling and conversion factors. So let's look at fractions practice. In this example, we've got a large cake. It's cut into 48 pieces for an anniversary celebration at a utility. A third of the cake was brought back to the water office. And at the water office, the operators ate half of what was brought back. What portion of the cake was eaten by the water operators? So if we know we have half of the cake, or a third of the cake was taken back, and they ate half of it, we can simply multiply the half that was eaten at the water office by the third that was brought back. And that'll tell us that at the water office, they ate 1/6 of the entire cake. Well, if there's 48 pieces, 1/6 of that is 8 pieces. Simply 48 divided by 6. So that tells us how much they ate. Now, another third of that entire 48-piece cake was eaten by the wastewater operators. So we can figure out the total proportion of the cake that was consumed by both water and wastewater operators. We do that, we're going to take the 1/6 that we had from the water operators, and we're going to take the 1/3 that we had from the wastewater operators, and we're going to add those together. Now we need to have common denominators. So in order to do that, we're going to multiply the 1/3 by 2/2. That's going to give us a denominator of 6, which matches up with the 1/6 that we had from the water operators. So if we do that, we're going to multiply to get the same denominator. And so we'll have 1/6 plus 2/6. So 1 times 2 is 2, 3 times 2 is 6. So we can add those together. If we do so, we get 3/6. And we can reduce that by dividing both the top and the bottom by 3. That's a common factor there. And doing it, we realize that half of the cake, half of the 48-piece cake was eaten by the water and wastewater operators. So 24 pieces of the cake were eaten. All right, so another important concept in water math is flow. So flow can be represented in a bunch of different ways. Here we're showing gallons per minute. So flow is is a volume over a time. So in this case, the volume is gallons, the time is minutes. We can also have it in gallons per day. Volume being gallons, the time being day. We could have it in million gallons per day, or MGD. We can also have it in units such as cubic feet per second. So cubic feet being the volume, seconds being the time. So we can look at a practice problem here. If we've got a pump and it fills a 500-gallon tank in 4 minutes, what's the flow that's delivered in gallons per minute? Okay, so we've got 500 gallons, 4 minutes. What's it in gallons per minute? Well, it's simply taking the number of gallons that we have and dividing it by the number of minutes, and that's going to give you your GPM, or gallons per minute. It can be expressed as a fraction. We're gonna do that here. So if you take our 500 gallons over 4 minutes, we don't cancel out because the units aren't the same, so we can't cancel out. If we do that, we determine that there's 125 gallons per minute being put out by that. That's the flow delivered by that pump. Now, if we're curious, okay, so we've got a pump that pumps 125 gallons per minute. Well, how many gallons would it pump in an entire 24-hour day? We'll look at that next. So if a pump has an output of 125 gallons per minute, what is the output in both gallons per day and million gallons per day? All right. So first of all, if we're going to go from minutes to day, we need to know how many minutes are in a day in order that'll be our first conversion that we're going to do. So if we know there's 24 hours in a day and there's 60 minutes in an hour. If we multiply those together, the hours cancel out, and that gives us something. It gives us minutes are going to be on the top and days are on the bottom. All right. We multiply the 24 by the 60, and we get 1,440 minutes per day. So that's how many minutes are in an entire day. And that's something, I believe that's on your formula sheet. We could go through and we could do these calculations each time. I think that the majority of and I honestly, that's how I would probably do it. I would start and I would longhand, I'd do all of these out. But this is a conversion factor in and of itself. We know there's 1,440 minutes a day, and we'll use that as kind of a shortening of our problems throughout this training. So if we want to go to gallons per day, we're going to take our 125 gallons per minute, and we're going to multiply that by the number of minutes per day. And as you'll see, the units are going to cancel out here. Our minutes cancel out. We've got minutes on the top. We've got minutes on the bottom. They cancel out. And we're given an answer that's in gallons per day. And it's simply 125 times 1,440. And that's 180,000 gallons a day. So now if we want to know the million gallons a day, we're going to need to divide the number of gallons per day by a million. And this 1 million gallons per mg is really dividing by 1. mg stands for million gallons. 1,000 gallons is million gallons written out. And what it does is it also cancels. It cancels the gallons out, and this is per million gallons, so that brings that up to the top. The mg comes up to the top, and we'll have a result of mg per day. If we do that, we end up with 0.18 mgd. So 180,000 gallons a day is 0.18 mgd. It's simply taking and dividing that by a million. All right, we've got a water treatment plant that treats 2.5 mgd, million gallons per day. What's the flow rate of this plant in gallons per minute? So now we're going to go from million gallons a day and down to gallons per minute. So if you would expect, first of all, that that number is going to get larger because we're going to have more gallons than we did in that million gallons. So to convert to gallons per day, we're going to take our 2.5 MGD. We're going to multiply that by a million gallons per mg, which I said that's basically multiplying it by 1. It cancels out our mg's, and it just gives us an answer in gallons per day. So it's 2.5 times a million, or 2,500,000 gallons per day. Now, we have that in gallons per day, but we want our answer in gallons per minute. So we're going to have to do a conversion that takes us from days to minutes. So we'll divide by the minutes in a day. And as we had said, there's 1,440 minutes in a day. So if we take our 2,500,000 gallons, we divide that by the 1,440 minutes. We could have also gone through and said, we're going to take that to the number of hours in a day and the number of minutes in an hour. We could have gone through that process, but this is just, as I said, this is a shortcut here to get to minutes. If we do that, we get 1,736 gallons per minute. We want to look at this as all one big calculation. We can do that. So it's our 2.5 MGD times a million gallons per mg divided by 1,440 minutes per day. The mg's cancel out. And the days might not. Oh, I'm using the cursor on the wrong slide. Sorry. So that gives us the same answer, and it's 7.36 gallons per minute. Okay, so we're up to our first poll question. So we've got a high surface service pump delivers 1,200 gallons per minute. Convert the flow rate to units of million gallons per day. So we'll give everybody a few minutes to do the poll, and then I'll work the problem. All right, Scott, can you close the poll, please? Or I can do it, I guess. I'm sorry. And when it comes to these polls, I apologize if we close them before you get done. We just at some point we need to keep moving along. So I will look to work the problem here. So we had a high service pump delivering 1,200 gallons per minute, and we want to convert this flow to units of million gallons per day. So we're going to take our 1,200 gallons per minute. We're going to multiply that by the number of minutes in a day, which is 1440. And then we're going to divide that by our 1 million gallons per mg. So in this case, our gallons are going to cancel out. Our minutes are going to cancel out. Our mg is going to move to the top of the equation. And that's going to just give us 1.73 mgd. Okay, so that was response. I will share the results with you. And 87% of the people had 1.73, 13% had 0.23 mgd. Okay. So that's our first poll question. So we move along here, and yes, 1.73 mgd is the correct answer. And there's our little pumping water. So now we're going to go into some basic geometry concepts. We're going to look at area of rectangles. We're going to look at rectangular volume. We'll talk about areas of circles, perimeters, circumference, cylinder volumes, and we'll also get into some areas of triangles. So area of rectangles and volume of rectangles, the area is simply the length times the width. And if we want to calculate the volume, we're going to throw in the third dimension. In this case, it could be height, depending on how our things set up. We're simply going to multiply. Volume is going to be the length times the width, which is the area, times the height. So let's look at this problem we have here. We've got, we're saying area is used for process control calculations for filtration rates and sedimentation basin loadings. So if we've got a rapid sand filter, it's got a width of 10 feet and it's got a length of 20 feet. What's the area of the filter in square feet? Well, we said area is equal to length times width. So that's simply the 20 feet times the 10 feet, or we have 200 square feet of area on our sand filter. And we're going to square those. We need to carry those units through because quite often for our calculations, it becomes very important. All right, so we're already back to another poll question. In this case, we've got a rectangular sedimentation basin that's 80 feet long and 20 feet wide. We need to calculate the total surface area in square feet. Start with the poll. Okay. We're going to end the poll, and I will go over the problem. So in our rectangular sud basin, it's 80 feet long and 20 feet wide. We want to know the total surface area. So remember that area is equal to the length times the width. So in this case, area is equal to 80 feet times the width of 20 feet. So that gives us 1,600 square feet. Whoops. Me and pens do not typically work out very well. Okay, so we will share the results of the poll. 100% of the people that responded, which was 82% overall of the overall people, said 1,600 square feet. All right, well, I'm probably making these too easy. They will get more difficult as we go along. Sedimentation hydraulic loading is measured in gallons per minute per square feet. So that's going to be an important thing. That's a good reason why we need to know this. And it's called the overflow rate. The design overflow rates for sud basins are typically from 0.5 to 1 gallon per minute per square foot. All right, so next we're going to look at area formulas for circles. So if we want to figure out the area of a circle, we can imagine that we've got a square that's around that circle. And each side is equal to the diameter of the circle. So the area of a square, that square that's in red, would be d squared in this case. The area of the circle is 0.785 times d squared. So it's 78.5%. The area of the circle is 78.5% of the area of the square. And so we're going to use that 0.785 times d squared as one of our formulas to determine the area of the circle. All right, we can also, I know the 0.785 times d squared is something that, as far as the area of a circle, is something that you should probably memorize. It should be on your formula sheet that we sent out. But I had from the realm where I learned that the area of a circle is pi times the radius squared. And so in this example, we're showing that the area of this square here is 3.14 times, or that the area of that as a square would be r squared, and the area of the circle as a whole is 3.1 times that r squared. You can use either one of these. It's up to you. But as you'll see, it seems like the diameter, in a lot of the problems that will work, there's a need to have the diameter anyhow. And so I've converted to the 0.785 times d squared versus the pi r squared myself. So now we're going to talk about a circular sedimentation basin. So that circular sedimentation basin has a diameter of 50 feet. And we want to know the surface area in square feet. So we're going to have to figure out what the area of the circle is. So we can use that pi r squared. We'll go through that. We'll do this example both ways. So if we're going to take pi, it's a number that goes on forever, but for most of our calculations and the accuracy that we need, 3.14 typically works. So if we take our 3.14 and we multiply that by the radius, in this case, we need half of the diameter because we're using pi r squared. We multiply that by the radius twice, and we get 1,962.5 square feet. So this is where pi is approximately 3.14. If you use pi on your calculator, it's going to be a really long number, and it's going to affect your answer compared to what what we're working at when we use just 3.14. So it's non-repeating decimal that goes out many places. If you wanted to use the area is equal to 0.785 times d squared, you simply take that 0.785, you multiply it by diameter, and then again by the diameter. In this case, it's 0.785 times 50 times 50, and lo and behold, we get that same answer. And there's a note that 0.785 is 1/4 of pi. So if you took pi and you divided it by 4, you're going to find that you get 0.785. So on the bottom, we've got pi r squared is equal to 3.14 times the half of the diameter times half of the diameter. And if we simplified that, it would be, we could multiply the 1/2 by 1/2 is going to give us a 1/4. So it's 3.14 times 1/4 times the d squared. And lo and behold, that equals 0.785 times d squared. There's a lot of people that have confusion as to why we can use 0.785 d squared. This is hopefully to explain why we can do it. It's up to you as to which version, whether you want to use pi r squared, if you want to use 0.785 times d squared. All right, so we've got a practice problem. We want to calculate the cross-sectional area of a 12-inch diameter water main in both inches and square feet. Okay, so if we use area is equal to 0.785 times d squared in inches, we're going to have to do a conversion. Or no, we won't have to do a conversion. We will when we get to feet, excuse me. So 0.785 times 12 inches times 12 inches. If we do that calculation, we should see 113.04 square inches. If we want to look at that in feet, we're going to have to do that conversion on the 12 inches. So we're going to divide the 12 inches by 12 to get feet. So there's 1 foot in every 12 inches. We're going to put that into our area is equal to 0.785 times d squared. We do that, and we get an area in square feet of 0.785 square feet. You could have also, if you chose, you could have used 144 square inches and a square foot as a conversion factor to go from area in square inches to area in square feet. So that would have been an option as well. And to do that, we take that 113.04 square inches, we'll multiply that by 1 square foot per 144 square inches, so that our square inches cancel out, and we're left with something in square feet, 0.785. So the math works out. All right. So next, we're going to look at perimeter and circumference. So perimeter is the total length of the sides of a shape. So it's adding up all sides together. For a circle, it's that outer, all the way around. Not very good putting up a circle like that. But for a rectangle, it's the sum of all 4 sides. So the perimeter is equal to 2 times the width plus 2 times the length. Now a circle, we're just talking about that circumference, that area around the circle. And for that, we've got a formula. Remember, circumference is equal to pi times diameter. Could also be considered equal to pi times 2 times the radius as well. So if we take our circumference is equal to 3.14 times the diameter, we can use that for getting the circumference of the circle. And it's important, it'll come into play, we'll see this later on. If we've got, especially if we have a circular said basin. We may be concerned about the weir overflow rates. If we had a circular tank and we wanted to put a circular fence around it, we might be concerned with how long that fence needs to be. Same thing, if it's a rectangle or a square, we may need to calculate these things. So we've got a practice problem with, in this example, we've got a rectangular city lot. It's owned by a utility. The lot measures 125 feet wide by 200 feet deep. And we want to put a security fence around the perimeter. We want to estimate the cost of the fence. Based on a quote that we had, that's $29 per linear foot for installing a 6-foot high security fence. So we want to put this fence up. We want to know what it's going to cost us. So here's, this could be our site. We've got a storage tank. We've got a well. The site that needs to be fenced is 125 by 200. So first thing we want to do is we want to figure out what the perimeter is. So if you simply went and added those together, you would take the 125 feet on the left side, the 125 feet on the right, the 200 feet on the top, the 200 feet on the bottom of the diagram. If we add those all together, we're going to get 650 feet. Now, the other way we could go about this is we could use that formula for perimeter. It's 2 times the width times 2 times the length. So in this case, it's 2 times 125 feet plus 2 times 200 feet. And lo and behold, we get the same answer. Now, as far as the cost goes, we know that it costs $29 per linear foot. And we know that we have 650 feet. So if we take and multiply that 650 feet by the cost per foot, in this case, our feet are going to cancel out and we're going to be left with just dollars. We do that multiplication, 650 by 29, and that gives us 18,850 feet. Okay. Yeah, and a lot of utilities will use, cost per foot basis when they're trying to estimate what it could cost to have water main installed. So, that concept of the number of feet and the cost per feet to figure out what the total cost would be can be important. All right, so now we're on to our next poll. In this poll, we've got a circular clarifier. It's 60 feet in diameter, and it uses a peripheral weir. So there's a weir around the outside that with a length equal to the tank's perimeter. Calculate the surface area of the basin and the total length of the weir in feet. Whoops. Oh, that's okay. Those are our options. I'm sorry. All right. Thank you, Scott, for putting up the poll. All right, I'm ending the poll. Just so you know, we try to get somewhere around 75 to 80% of the people responding so that we can that's our goal before we end the poll. All right, so let's look at this problem. So we've got a circular clarifier. It's 60 feet in diameter, and it uses a weir on the outside with a length that's equal to the tank's perimeter. You want to know the surface area of the basin and the total length of the weir in feet. So we're going to need to determine the area. Okay, so the area is equal to 0.785 times the diameter squared. So we put in our numbers. The diameter in this case is 60 feet times 60 feet. We work that out, and I get 2,826 square feet, or feet squared, whichever one you want. Now, for the length of the weir, we're gonna use our circumference is equal to 3.14 times the diameter. 3.14 times 60 feet. And that gives us, hopefully everybody can see what I'm writing, 188.4 feet. Okay, so that corresponds, we'll share the results here. 86% of the respondents said C, 2,826 square feet, and a weir length of 188.4, and we had 14% with B. All right. So yeah, that's C is the correct answer. All right. So now we're going to talk about the area of a triangle. This is much less likely to come into play, but it's good information to have. So the area of a triangle is 1/2 the base times the height. So it's like taking our square and cutting it in half. So normally we would have length times width, the same as height times base, but we're only going to take half of that when it comes to a triangle. So we've got an example. We have an area of land is in the shape of a triangle that has a height of 100 feet and a base of 60 feet. What is the area in square feet? And we take our area is equal to 1/2 times the base times the height, and we calculate that out. 1/2 times 60 times 100 gives us 3,000 square feet. Now, if you want to know the length of C, we have to use something. What C would be considered the hypotenuse of a right triangle, and this only works for right triangles. But we can use the Pythagorean theorem, which is it says that a squared plus b squared is equal to c squared. So the square of the base plus the square of the height is equal to the square of the hypotenuse, the long side in this triangle. And in order to calculate what the hypotenuse is, we're going to have to use square root. So we're going to say that C is equal to the square root of a squared plus b squared. That's simply taking our a squared plus b squared equals c squared, taking the square root of each side, and that gives us the C is equal to the square root of a squared plus b squared. So if we, in this example, if we put in our numbers, so C is going to be equal to 100 squared plus 60 squared. We calculate that out, and that's going to give us the square root of 13,600, which is equal to 116.62 feet. And maybe there's some instances that you can think of that this might be important. I know I think back to time that I spent with the community that I worked with, we had some properties that were along a railroad, and a railroad transversed. It wasn't perpendicular to the road, so we'd have properties that would be shaped like this. So if, for instance, we wanted to put a fence up around it, that might be something that we would need to know. So we're on to our next poll already. In this poll, we've got a triangular parcel at the corner of a water plant property. It's got a base of 150 feet and a height of 90 feet. The utility officials want to install a special type of permeable concrete over the parcel to capture rainwater rather than allow it to run off. To get a cost estimate, they need to know the area. So calculate the area in square feet. And if you're so inclined, we have a bonus question. You can also determine what the perimeter is of this parcel. The poll, thank you. Yeah, we're backed up to 29, so it's whoever left back. What's that?
Greg is,
Oh, is that who it was?
no, no, he comes to the panel, it's not as funny.
Oh, good. Okay, we're gonna end the poll and I will work the problem. By the way, if you did calculate the perimeter and you'd like to put your response into the chat, that would be good. We'll look at those here. Okay, so triangular parcel, base of 150, height of 90. We want to calculate the area in square feet. So our area is equal to 1/2 times the base times the height. So 0.5 times 150 feet times 90 feet. We multiply that out and we get 6,750 square feet. Okay. What are we getting for responses for the perimeter in the chat? Okay, 480. I'm jotting down some numbers.
We have 429.7,
Okay,
and we have two people that says 415.
415. Okay, well, they're all pretty close to the same. They're all in the fours. So if we look at this, perimeter is going to be equal to the square root of the 150 squared plus the 90 squared. So that's the square root of 30,600. You do the square root of put that into your calculator. I get 174.93 feet. We add 150 plus 90 plus 174.93. I get 414.93 feet. And so in this case, obviously the 415 is correct. It's just an error issue of, to what degree you rounded. So good. It's all good. So let's move on here. The answer. So we'll share the results. And 83% said 6,750 square feet for the area. We had 17% at 13,500. All right, and 6,750 square feet is the correct answer. This is just working of the problem. All right. So on to another problem. We've got a circular groundwater storage tank with a diameter of 40 feet and a height of 25 feet. If a gallon of coating material covers 250 feet and each gallon costs $125, what is the total material cost to coat the entire tank interior? So we've got a few things going on here. We need to know what we got to know the perimeter in order to determine some things. We need to know the area of the tank wall. And the area of the tank wall, so we're going to take that area of the tank wall is going to be the length of the circumference of the wall times the height of the wall. So so if we take, and we're going to spread that, we're going to, like, in essence, we're going to cut the wall of that tank in half, and we're going to spread it out so we get the entire length of it. And that's going to be the area is the length times the height, 3.14 times 40, that's the length, and then the height is 25 feet. So this 3.14 times the diameter is going to tell us that's basically the circumference, because we need to know the total inside of the tank, and then we're going to multiply that by 25, the height of the tank. So if we do that, that tells us that inside tank wall is 3,140 square feet. Now we also have to take into account both the floor and the roof. All right, so that's going to be our 0.785 times the diameter squared. That'll give you the area of one of them, and then we'll double that in order to figure out what the total is. So if we multiply 0.785 times 40 times 40, that gives us 1,256 square feet. But to know the total interior area, the walls, the roof, the floor, we need to add that 3,140 square feet to the floor at 1,256 and the roof at 1,256. And so that's going to give us a total interior area of 5,652 square feet. Now, we know that for a gallon of the coating material covers 250 square feet. So we can take, to determine the number of gallons of material that we need, we'll take our total square foot area and we'll divide that by the square foot per gallon. So 5,652 square feet divided by 250 square feet per gallon. The square feet are going to cancel out and the gallons will go to the top. So it'll give us the number of gallons that we need to collect, or we need to have to do this project. So it's 22.6 gallons. But we're not done yet because we want to know what the cost is. So if we need 22.6 gallons, it's $125 a gallon. So we multiply the 22.6 gallons by $125 per gallon. The gallons cancel out and we're left with something in dollars. So that's $2,825. And that's just the cost of the actual paint. There's going to be other things to consider on a project like this. You know, what's labor, safety equipment, what, you know, the brushes, rollers, things of that nature. And the other thing to consider with this is that you're probably not going to be able to buy, you know, exactly 22.6 gallons. Your chances are you're going to have, you know, more gallon, you know, if you can buy it by the gallon, if you're buying it by the 5-gallon pail, you need to consider that when you're thinking about it as end costs. All right, so the next thing we're going to look at that comes up probably not as often, but it's another potential math concept when it comes to water is acres. We're going to look at area in acres. An acre is equal to 43,560 square feet. So an acre is actually 660 feet by 66 feet. Now, that's how they were derived initially. It's an Old English surveying measurement. There's some crazy stuff that goes along with this, and we'll look at it just because it's kind of neat to know. You know, they started with chains, and so they were trying to avoid the idea of having decimals. So they came up with this chain. Well, it's crazy that a chain is like 7.92 inches long. It seems pretty arbitrary, but so one chain one link is 7.92 inches long, and there's 100 links in a chain, and there's 10 chains equal a furlong. So one chain of 66 feet multiplied by a furlong of 660 feet gives us this acre. So this in theory is, this acre here is a chain by a furlong. Just a whole nother, the important thing for us to remember is really the number of square feet in an acre. But so there's, you know, if we want to look at this, there's also 80 chains in a mile. So 80 times 666 gives us the 5,280 feet. So if you're wondering why a mile is 5,280 feet, that's probably got something to do with the fact that there's this system of chains and links and furlongs and acres. You can go through those in the calculator, but you know, furlongs, what comes to mind to me is when we're, you know, horse races, you know, so they still utilize furlongs. So if you ever wondered what a furlong is, that's 660 feet. So we're going to go to a poll. Remember, we said there's 43,560 square feet in an acre. In our poll here, we've got a surface water reservoir. It's 150 feet by 500 feet. And what is the area of the reservoir in acres? Thank you, Scott. All right, we're over 70, up to 80% of people responded. So I'm going to end the poll and then I'll go over the problem. So in this problem, we've got a surface water reservoir that's 100 or 1,500 feet long by 500 feet wide. What's the area of this reservoir in acres? Slide it down. Can't see it. Okay. Thank you, Ingrid. Okay, so the area in square feet is going to be the 1,500 feet. We're going to multiply that by the 500 feet. So that's the length of the reservoir multiplied by the width of the reservoir. And that gives us 750,000 square feet. Now we need to convert to area or to acres, convert our area to acres. So if we take our 750,000 square feet, and we know that there's 43,560 square feet in an acre. So I want acres and I want to get rid of square feet. So I'm going to put the acres on the top. So that's 1 acre, and that's equivalent to 43,560 square feet. Okay. So if we divide 750 by 43,560, our square feet are going to cancel out and we'll be left with something in acres. If I do that, I get 7.2 acres. Okay, so I will share the results of the poll. And in this we have 83% of the respondents said 17.2 acres. Okay. We had 8% at 750,000 acres. Probably didn't go through and divide by the number, or by the 43,560 square feet per acre. And then we have 4% at both 17,200 and at 7,501. Okay. And 17.2 acres is the correct answer as we stated. So there's a solution of that. So next we're going to go into, we're going to talk about volume a little more. As we had said, volume is important because it's, we look at flows are volume divided by time. So it's important for many reasons to know volume, but that's one of them. So we'll take a rectangular basin that's 60 feet long, 20 feet wide, and 12 feet deep, and we want to determine the volume in cubic feet. So if you recall, volume is length times width times height. In this example, we've got 60 feet times 20 feet times 12 feet, and it gives us 14,400 cubic feet. So what would we need to do if we want volume in gallons? Okay, so this is, we're going to take and multiply the number of gallons that we have by the number of gallons in a cubic foot. So gallons per cubic foot is the next concept that we're going to cover. And in this example, there's 7.48 gallons in each cubic foot. That one always baffles me. It seems like that's cubic foot. It's hard to imagine that there's almost seven and a half gallons of water would fill that space, but that's what it is. So of an example, we have a tank that measures 4 feet wide, 5 feet long, and 6 feet high. What's the volume of this tank in gallons? So we use we're going to calculate the volume in cubic feet first, and then we're going to do a conversion because our units are all in feet. So if we take our volume is equal to 5 feet times 4 feet times 6 feet, we get a total of 120 cubic feet. So the next step is we want to do that conversion. We want to convert from cubic feet to gallons. And we're going to do that by multiplying by 7.48 gallons per cubic foot. So we take our cubic feet, 120 cubic feet multiplied by 7.48 gallons per cubic feet. You'll see that the cubic feet are going to cancel, and we'll be left with a unit of just gallons. And it's going to be 120 times 7.48, or 897.6 gallons. All right, so our next concept is going to be million gallons. And we're going to jump right to a pole. And that pole is a rectangular reservoir. It's 200 feet long, but 100 feet wide and 15 feet deep. Calculate the total capacity in million gallons. I'll make you jump right into million gallons. We had talked about a little bit earlier. So Scott, if you could put up our poll for us. All right, so the poll started. so we are going to end the poll. And I will work the problem. All right, so we've got a rectangular reservoir. It's 200 feet long, 100 feet wide, and 15 feet deep. We want to know what's the capacity in million gallons. So first of all, we want to determine the volume, and we're going to determine the volume in cubic feet to start with, and then we're going to make a conversion into gallons, and then we'll convert into million gallons. So if we take our volume is equal to 200 feet times 100 feet times 15 feet. Okay. And then we're going to take and multiply that. That'll give us something in cubic feet. And then we're going to multiply that by 7.48 gallons per cubic feet. So what that's going to do, everybody can hopefully see this, it's going to cancel our feet out, and that'll give us an answer in gallons. And then we're going to take that and we're going to divide that by a million. So 200 times 100 times 15 times 7.48, I believe should be, whoops, everybody just saw my pen. I think it just is not, hopefully it's just not, it'll work. So that should be 2,240,000 gallons. Divide that by a million gallons per mg. The gallons will cancel out. Oh, I'm going to have to, is this one? Hopefully it's black. So the mg will go to the top, and that'll give us 2.24 mg, million gallons. All right. Let's see how let's share the results. And we have 83% of respondents at 2.24. We had 13% at 0.298 and 4% at 224 million gallons. Okay. And this is the solution that you'll see in your the slides that get links sent out for those. All right. So now I think we'll take I'm going to take a 15-minute break. This training had 15-minute breaks set up, so I think we're doing well on time. We'll take that break now. So we will be back at 10:45 Eastern time. Well, I hope everybody had a good little break there and enjoyed the video feed of our campus here at Michigan Tech. So yeah, this it was a little bit of a zinger throwing in the million gallons, but really it's just another conversion, pretty minor one at that. So hopefully everybody did okay with that. So we're gonna look further on in volume. We're gonna look at volumes of cylinders, which, as you can imagine, are very important. There's a lot of cylindrical tanks out there. Water mains obviously are one of the more important things that we deal with in the water industry, and those those pipes we need to know cylindrical volume in order to determine the volume of those pipes as well. So it's the volume of a cylinder can be thought of as the circular cross-sectional area. And then we're going to add in the dimension of length or height, depending on how it sits. It's basically the same thing. It's just, is it standing upright? Is it laying down? That's the only thing that changes. All right, so volume in cubic feet is going to be equal to 0.785 times that diameter, times the diameter again, and then times the length or the height. And that's going to give us units that are in cubic feet in this case. So let's look at our practice problem. We've got a cylindrical tank that has a radius of 15 feet and is filled to a height of 20 feet. And we want to know the number of, or how many gallons are in it. What's the volume in gallons? So the first thing we're going to have to do is we're going to have to determine the volume in cubic feet, but we're going to do that conversion in radius to diameter just because they gave it to us in the radius, which simply doubling the radius gives us that diameter. But then we're going to have to do a formula for determining the cubic feet and then converting from cubic feet into gallons. So our formula for the volume in cubic feet is that 0.785 times d squared times 7.48, or excuse me, times the height. So that's going to be the volume, 0.785 times d squared times height. That gives us the volume in cubic feet. And then we're going to use our 7.48 gallons per cubic feet to convert that into gallons. So we put those numbers in, 0.785 times 30 feet, times 30 feet, times 20 feet, times the 7.48. This formula is shown is not really very consistent. We should have had all the units in there, but what ends up happening is the cubic feet cancel out and we're left with gallons. 105.692 gallons, or approximately 106,000 gallons. 105,692. So another way we could have looked at it, if we wanted to use the used pi, we could take and determine the area as pi times r squared, and then multiply by that height. That's going to give us the volume, and then we'll multiply by 7.48 gallons per cubic foot. And regardless, it gives us pretty much the same answer. It does give us the same answer, depending on rounding. All right, so we're going to jump right into a pole with cylindrical volume. We're looking at a cylindrical storage tank that's got a diameter of 40 feet and a height of 30 feet. And we need to know the total capacity in gallons. So Scott will bring up the pole. Thank you, Scott. Okay, well, I will end the poll. And I'll work the problem. All right, so we have a cylindrical storage tank with a diameter of 40 feet, a height of 30 feet. We want to know the total capacity in gallons. So the first thing that I would do is determine the volume. So that's going to be our 0.785 times the diameter squared. So the diameter is 40 feet times 40 feet. And then it's multiplied by the height of 30 feet. Okay. Then we're going to take that and we will then multiply it by the 7.48. Hopefully, we're not running off the paper here. 7.48 gallons per cubic feet. I will try better to not have this work out this way. But as you see, the cubic feet and the feet cancel out. And that gives us an answer of 281, 846. And if you wanted to know what that was in million gallons, you simply divide by a million, and that's going to be 0.2822, depending on your rounding, million gallons. All right. So let's share the results of the poll, see what we have. We had 86% of the people said 281, 846, 9% 37,680, and 5% 7,046.2, I believe it is. Okay. All right. B is the correct answer. Here's the solution on the slides. Those are looking at the slides. So let's look at this as far as a pipe goes. So we're installing a new water main. It's 1,000 feet long. It's 8-inch diameter pipe. Calculate the total volume of water the pipe holds in gallons. This could be important if you're chlorinating to disinfect this water main as it's installed new. You would want to know how much water is in there, so you could do a calculation to make sure that your concentration of chlorine is appropriate to disinfect that water main as you're installing it, or after you've installed it and before you put it into service. So it's pretty much the same. We're going to take the volume is equal to 0.785 times the diameter squared times the height, and then multiplied by 7.48 gallons per cubic feet. The first thing we need to do is this was given to us in a diameter in inches. So we would want to convert that to feet to start with. We do that, we divide 8 inches by 12 inches in a foot, and that gives us 0.667 feet. So that's our diameter that we're going to plug in. So for a volume formula, we're going to take 0.785, multiply that by the 0.667 squared, or multiply it together twice. Then by the length of pipe, which is 1,000 feet, and then times 7.48 gallons per cubic feet. The cubic feet cancel out, and we're left with units in gallons. We do that calculation, we get 2,612 gallons. All right, well, we just worked a couple problems and we're already back to a poll. So in this poll, we've got a well casing. It's 10-inch diameter. It's 300 feet of water column, and we want to know the total volume of water held in the casing in gallons. Thank you, Scott. All right, so I will end the poll. And then I will work the problem. Okay, so well casing with 10-inch that's 10-inch diameter and it has a 300-foot deep water column. We want to know the total volume held in the casing in gallons. And why might we want to know this? With wells, there's times where we may need, say we just had some work done on the well was pulled. We may want to chlorinate it to make sure that there's no contamination, no coliform bacteria or anything like that. So that's there comes times where we would want to know this information so that we can properly do things like chlorinating a well. So the first thing that I would look to do is we need to make sure that we have our diameter in feet. So we have 10 inches. We divide that by the 12 inches in a foot, and that's going to give us 0.833 feet for our diameter. So then we take our volume is equal to our 0.785 times the 0.833 feet times 0.833 feet times 300 feet. So that's going to give us a volume that's equal to 163.4 cubic feet. Now we take that 163.4 cubic feet. We're going to multiply that by 7.48 gallons per cubic foot. Our cubic feet cancel. And the resulting answer is 1,222.3 gallons. Okay. So now I'll share the results of the poll. And wow, everybody who responded said 1,222.3 gallons. So I'm not sure if I'm explaining it right or you guys are just getting it, but good job. All right, so we will, and 1,222.3. Here's the slide a slide that explains that, those results. As I said, you may want to know that information could be important for doing things such as shock chlorination, disinfecting that well. And it's important to know not the total length of the casing, because you don't want to chlorinate the part that doesn't have any water in it. You don't want to add that chlorine. You want to know the actual depth of the water in the casing. So next we're going to talk about the weight of water. So this is a pretty common thing. People estimate water weighs around 8 pounds. It's actually closer to 8.34 pounds per gallon. But what is the weight of 1 cubic foot of water? What's that weight for 1 cubic foot? And as you recall, I had said that we've used this conversion factor. There's 7.48 gallons in 1 cubic feet. And if we know that there's 8.34 pounds per gallon, we can use those to figure it out. So what is the weight of 1 cubic feet of water? We take a cubic foot of water, we multiply that by the 7.48 gallons per cubic feet. So that's going to get rid of our cubic feet and give us just gallons. And then we can multiply that by 8.34 pounds per gallon, which we just it said there's 8.34 pounds per gallon. That's going to get rid of our gallons, and it's going to give us an answer that's in feet. So that's 62.3832 pounds, or more commonly noted as 62.4 pounds. So there's 62.4 pounds per gallon, there's 7.34 gallons per cubic feet, and there's 8.34 pounds per gallon. So those are the three. And if you've got 2 of those, in theory, you can calculate out the third. If you have 2, you can get the third. So now we're gonna use we're gonna do a poll where we look at um, the um, the volume and we try to determine the weight. So we're going to take all these things these things we talked together. We're going to put them together for this poll. And in the poll, we've got a cylindrical barrel with a diameter of 21 inches. It's filled to a height of 33 inches. I'm going to estimate the weight of the water in the barrel. Okay, thank you, Scott. Poll's up there, and I'll work the problem after you guys have a chance. Okay. All right, I'm going to end the poll and we'll work the problem. So we have a cylindrical barrel. It's a diameter of 21 inches. It's filled to a height of 33 inches. Estimate the weight of water in this barrel. So we're going to want that in pounds. The first thing that we need to do is we're given stuff in inches and we want to get it to feet so that we can do our calculation in cubic feet. So if we take our 21 inches, divide that by 12, we take our 33 inches, divide that by 12, and we get 1.75 feet, and we get 2.75 feet. Okay, so now we're going to take that, our volume is equal to 0.785 times the diameter squared, which is 1.75 feet times 1.75 feet. And then we're going to multiply that by the height of 2.75 feet. So if we do that calculation, we're going to get 6.611 cubic feet. Okay. Now what I would do is I would take that 6.61 cubic feet, 6.611. I'm going to multiply that by 7.48 gallons per cubic foot. That gets rid of our cubic feet, gives us an answer in gallons, which is 49.45 gallons. And then we can take their 49.45 gallons, and we can use our conversion of 8.34 pounds per gallon. The gallons will cancel out, and we're going to get an answer that's in just pounds of 412.4 pounds. So I'm interested, does anybody know what we could do to eliminate, to make this, instead of both of these steps, to just have one step? So anybody who knows what that would be wants to put it in the chat. If you don't know, I will show anyhow, but all right. Yeah. So Jamel says 62.4. So yeah, that's it. So what I would have probably done to simplify this problem is to take the number of cubic feet that we had, 6.611 cubic feet. I'd multiply that by 62.4 pounds per cubic feet. And I believe it gives an answer that is pretty much the same. It might vary by point something or other, but it's going to be pretty close to 412.4 pounds. So by using this conversion factor here, the 62.4 pounds per cubic feet, we don't have to go through one of the, we can shorten our calculation. So, all right. That's good. Let's see. I will share the results now. As you can see, 82% of the people who responded said 412.4. We also had responses for the others. So at 9, 5, and 5%, roughly. Okay, great. Let's, there we go. And here is the solution that goes along with your slides. So in our, we've covered that some weights for volumes. Let's see what we're going to talk now about. We're going to talk about some flow application problems. We're going to talk detention time, filtration rates, sedimentation basin overflows. First up, we have detention time. So detention time is it's the amount of time that the water spends, whether it's in a tank, it's in a process, if we're treating it in some way. It's important for sedimentation basins. It's important for if we're chlorinating and getting out chlorine having residual stuff like that. And for sedimentation basins, we're typically looking to a 3 to 4 hour time frame. So it's quite a while that water stays in that tank for 3 to 4 hours. It's quite a bit of time. If it's too short, some of the smaller stuff may not be effectively removed. So that's why it's important. The larger stuff will come out quickly, but we need that time in order to make sure that the smaller stuff comes out. So detention time is purely the volume in gallons divided by the flow in gallons per minute. So as you can imagine, we've seen where we've been given stuff that, a volume that could be in cubic feet. We've been given flows that could be in cubic feet per second. So in determining detention time, there's a good chance that we're going to have to manipulate what they give us, use some more conversion factors and things like that to get what we need in the end. So it's the plant flow. We've got that plant flow. We've got the volume in gallons. And the idea is how long does the water remain in the tank before it leaves the tank? So we can look at some examples. We've got a circular sedimentation basin. So the idea behind this is that the water comes up in the middle of the tank, and as it comes up, it's given time for the particles. They won't go over the weirs until they get to the outside, the edges, and so it gives it time for all those particles to settle out. In this photo, there's a V-notch weir. So the idea is that we're going to meter that water out on the in the low sides of those, and hopefully hold up any sediments from falling over. So it's going to require certain velocity to get over those. Orientation of the baffle, V-notch weir, and effluent. So the idea is that baffle makes the particles go underneath it, and then it goes up over and through the V-notch weir and into the effluent trough. So in theory, that water on the outside should be hopefully removed most of those sediments from it already. So if we want to talk about contact time for disinfection, which is typically we're considering chlorination when we talk about disinfection. So we use the same formula, but if we have to take into effect baffling factor, and sometimes we won't have a baffle, but if we do, we need to take that into account. And it's the idea behind a baffle is we want to avoid short circuiting. The last thing you would want is for somehow it to not spend the proper amount of time in the process, because it goes straight from where it enters straight to where it could exit. So it just goes straight through. So we'll put in baffles that'll make it go different routes, spend more time in the process or in the tank. So an example, we've got a flow of 500 gallons per minute. So that's on the bottom of our equation. And that flows through a chlorine contact basin with a volume of 50,000 gallons. So that's a volume on the top. And we've got a baffling factor of 0.5. We want to know what the chlorine contact time is. All right, so if we take our 50,000 gallons, which is our volume, we divide it by our 500 gallon per minute flow. Our gallons are going to cancel out. The minutes are going to be brought to the top of the equation because it's gallons per minute. They're on the bottom of a fraction on the bottom side. So they come up to the top. And so we'll get an answer in minutes. We multiply that out. 50,000 times 0.5 divided by 500. That gives us 50 minutes. All right, so we worked some problems. So now we're going to go to another pole. So in this pole, we've got a cylindrical sedimentation basin. It's got a diameter of 65 feet and a depth of 8 feet. The plant has a flow of 1.3 mgd. What is the detention time in hours? Thank you, Scott. Okay, I'm going to end the poll and work the problem. So cylindrical sedimentation basin has a diameter of 65 feet, a depth of 8 feet. Plant has a flow of 1.3 mgd. What's the detention time in hours? So this is a couple step problem. So the first thing that I'm going to do is I'm going to determine the basin volume in gallons. So we take our volume 0.785 times the diameter 65 feet times 65 feet times the height or depth of 8 feet. And that gives me 26,533 cubic feet, something along those lines. And then I'm going to take that 26,533 cubic feet, and I'm going to multiply that by 7.48 gallons per cubic feet. The cubic feet cancel. We're left with gallons. 198,466.8 gallons. The next step on the problem is we're going to need to convert our flow to gallons per hour. They give it in million gallons per day. We need it in gallons per hour. So we have 1.3 million gallons per day. That could also be written as 1.3 per day if we like. We're going to multiply that by a million gallons. Make sure I get my gallon per mg so that we can get rid of our mg and it'll just be gallons. And we can multiply that by 24 hours in a day. Since the day is on the bottom, it would cancel out with the day is on the bottom of the equation that's on the bottom. It cancels that out. And that gives us 54,166.7 gallons per hour. Okay. So if we remember our detention time formula is our volume divided by our flow. So in this case, our volume is 198,466.8 gallons, and our gallons per hour is 54,166.7. The gallons cancel out here. The hours, because it's in a fraction on the bottom side, the hours go to the top, and we end up with 3.66 hours. Okay. Share the results. And 80% agree with me at 3.66. We've got a couple people who said 0.27. We also have people that said 4.09 and 0.45. All right. There's the answer. Here is a solution that will be in the slides that you were presented. Okay, so the next concept that we want to talk about is overflow rate. So we've got a rate. The overflow rate compares the flow of the water applied to the basin to the basin's surface area. So how much water we got coming in over that area. Overflow rates are typically in gallons per minute per square feet. So we've got our flow in gallons per minute and divided by our area in square feet. Typically for overflow rates, we're looking at things in the half to 1 gallon per minute per square feet. But it can be higher. The overflow rates make sure that we have that sufficient settling time for smaller particles. You know, as I said before, the big particles are usually not the issue, it's the smaller ones. So we have to give them time. And as I said before, it flows from the center of a circular clarifier to the outside, to that edge weir, with the idea that in that time, it's going to, the particles will settle out. So as you can see here, the water comes in the center with the idea that as the water goes to the outside, these particles settle out. Small solids need sufficient time and low velocities to ensure settling in the tank. So low velocity is important. Low velocity means it's going to get a chance to spend a good deal of time to settle out. It'll have the time to make that happen. All right, practice problem. A cylindrical sedimentation basin has a diameter of 55 feet and receives a flow of 2,100 gallons per minute. What is the overflow rate? So we said before, the overflow rate is the flow in gallons per minute divided by the area in square feet. So if we we can figure out what the area is. So we take our 0.785 times 55, which is the diameter, times the diameter again, and that gives us approximately 2,374.6 square feet. So our overflow rate is our flow in gallons per minute divided by our area. So 2,100 GPM divided by 2,374.6 square feet gives us 0.88 gallons per minute per square foot. And that seems to be acceptable because it is within that half to 1 gallons per minute per square feet. So now we're going to give you a chance to do a problem on your own here with another poll. In this case, we've got a plant flow of 2 mgd. It's evenly divided between 2 rectangular sedimentation basins. Each basin is 65 feet long, 16 feet wide, and 12 feet deep. What is the overflow rate for each sedimentation basin? Thank you, Scott. Okay, in an effort to keep this rolling, we're going to end the poll and I will cover the solution to this. So this is it is a little worded a little tricky, I guess. So we got a plant flow of 2 million gallons a day that's evenly divided between two rectangular sedimentation basins. Each basin is 65 feet by 16 by 12. What is the overflow rate for each sedimentation basin? So you only have to look at one of them. So first of all, the area that we're going to look at is equal to 65 feet times 16 feet. The flow, or so that's going to be equal to let me get this. We're gonna, I gotta make sure I get my stuff right here. So the flow in gallons per minute is 1 million gallons, because you only have to look at one of the basins. And then if we take into account there's 1,440 minutes per day, that's going to give us an area that we applied that flow to of 1,040 square feet. We've got an area, an overflow rate. Let me see here. I got some numbers out of whack here. No, my numbers are off. So that area is 1040 square feet. And then this is going to give us 694.4 gallons per minute. And we take our 694.4 gallons per minute and we divide that by the area. Wow. And this stuff all messed up. And that gives us 0.67 gallons per minute per square foot. So it's important on this one to realize that this 2 million gallons is divided between two rectangular sedimentation basins. So that's where we get the 1 million gallons per day. So we don't have to worry about the 2 million. The area, because we're only looking at one basin, we're only looking at one area. So we don't have to double this. We're just looking at one. And then we're dividing the flow in gallons per minute by the square feet to get our 0.67. You could do this problem if you wanted to, but with using the 2 million gallons a day and doubling the basin area, but you don't have to. So, all right. So let's share the results of the poll. We had 74% had 0.67 gallons per minute per square foot. All right. There we go. And here is the probably a better version than what I provided of the solution to the problem. I'm not sure where I got derailed. Probably the last concept that we're going to talk about before taking a lunch break is the Weir overflow rate, the WOR. It's the flow in gallons per day per linear foot of Weir. So it's that flow rate that's going over that weir. So once again, we want to minimize the velocity. We want to keep it slow so that these things will settle out before they get to the weir. A design range for that is between 10,000 gallons per day per foot to 20,000 gallons per day per foot. All right, so for a circular weir, we've got a circular clarifier. It's got a diameter of 65 feet with plant flow of 1,550 gallons per minute. Calculate the WOR. So the first thing we want to do is we want to figure out the circumference of our clarifier. So if we remember, circumference is equal to 3.14 times the diameter. And if we calculate that out, we get 204.1 feet. Now, the next step we need to do is convert our flow from gallons per minute to gallons per day. And to do that, we take our 1,550 gallons per minute, we multiply it by the number of minutes in a day. So the minutes will cancel out. We'll be left with an answer in gallons per day, which is 2,232,000 gallons per day. All right, and then we're going to divide the flow that we have by the length of our weir, or the circumference of the clarifier. So we do that, we take our 2.232 million gallons per day, we divide that by our weir length of 204.1 feet, and that gives us 10,936 gallons per day per foot. And that overflow rate is in that area that we're the design area. So the next thing, we've got a poll. We'll do this poll, and we'll give till noon to do the poll, and then at noon we will put up the poll we need you guys to fill out over before lunch. So we've got a circular clarifier, a diameter of 55 feet. It's got a weir around its perimeter and receives a flow of 1.8 mgd. Determine the weir overflow rate for this basin. Thanks for putting that up, Scott. Ingrid, you can hold me on.
Sorry.
All right, I'll put up the slide that shows the weir overflow rate. If you've got your formula sheet, I believe this hopefully is in there. That might help with knowing what the formula is. All right, so you guys are jamming on this one. We're gonna end the poll. I'll cover this and then we'll put up that poll for the over lunch. And then you guys will be able to go after after that. So end the poll. So our circular clarifier, and you put, thank you, Ingrid. 55 feet of weir on its perimeter and then receives a flow of 1.8 mgd. We want to know the weir overflow rate. So the first step is to determine the circumference. So if we remember, C is equal to 3.14 times the 55-foot diameter, and that gives us 172.7 feet. Now we need to, the next step is we need to convert our flow to gallons per day. We were given in million gallons a day. So if we take our 1.8 million gallons per day, we multiply that by 1 million gallons per mg. So that's multiplying by 1 in essence. It gets rid of our mg's and it gives us 1,800,000 gallons per day. Now we need to divide the flow by the weir length in order to get the weir overflow rate. So if we do that, we take our 1,800,000 gallons per day. We divide that by 172.7 feet. And we get an answer of 10,423 gallons per day per feet. Okay, so I will share the results. And it looks like the majority of people also had 1,000 or 10,423 gallons per day per foot. Okay. Let me get back to, we'll go to the solution, as you can see. And then this solution will be in your, in the slide handout that was sent out, the PDF. So now we will take a break. We're going to be back at 1 p.m. Eastern time. And in the meantime, we would very much like you to fill out this poll over the break. Scott could put up our poll for us. Thank you very much, and we will see you at 1 p.m. Thank you all who filled out the poll. That's really, it's important that we gather that information. We need to report that as part of our contract to provide these free trainings. All right. So now we're gonna get through these next couple hours. Hopefully we get through quickly. We get you guys on with the rest of your day by 3 o'clock. The next topic that we are talking about is going to be filtration rates. And filtration rates are, we take the flow in gallons per minute, and that flow is going to be applied to the filters. There's the filter surface, and we want to look at the surface area in square feet of the filter. So we take the filtration rate is equal to the flow in gallons per minute divided by the area in square feet. Typically filtration rates for rapid gravity sand filters are in the 4 to 6 gallons per minute per square foot range. And then with these filters, to clean them out and make sure that they work efficiently, you have to backwash them. Let's see, Ingrid will work on the sound issue. All right. So backwash rate. Utilizing this filtration rate formula, we are going to go to a poll. So keep that formula in mind. In our pool, we've got a water treatment plant. It's got a flow of 6 million gallons a day. It's got 4 rapid sand gravity filters. Each one of those is 12 by 22. We want to know what the filtration rate is in gallons per minute per square foot for this plant. And one filter is taken offline for backwashing. The remaining 3 filters are operating. One of those 4 filters is offline. Thanks for putting this poll up, Scott.
Does that sound any better, guys?
Hello. We are working on the sound and we've got it figured out. Finish up getting responses to this poll, and then I'll cover the how to work the problem. Okay, we're going to stop the poll just to keep things rolling along, and I will work on the problem. All right, so we've got a treatment plant. It's got a flow of 6 million gallons a day, 4 rapid sand gravity filters that are 12 by 22. We want to know the filtration rate in GPM per square foot with 1 filter offline. And so based off the 3 remaining. So if we remember, our filtration rate was equal to our flow in GPM divided by the area in square feet. So first thing, we need to convert our flow to GPM. So we take our 6 million gallons per day. We divide that by the number of minutes in a day, 1440. Our days will cancel out. And that gives us 4,167 gallons per minute. All right, and then we have to determine the area of the filter. So if we take our 3 filters, we multiply that by 12 feet by 22 feet, and that gives us 792 square feet. Now we put our flow in, we put our area in. That's going to be 4,167 gallons per minute per, and then we're going to have the 792 square feet, and that works out to 5.26 gallons per minute per square foot. Okay, so I will share the results. And it looks like 79% of the people had that same answer. As you could see, the 2 of the answers were a little tricky in that those could have been things that you would have, whether you came up with the gallons per minute or the square feet, you could have come up with those answers by not totally doing the problem, by come up with a couple of the intermediate answers. All right, so hopefully everybody can hear me now. 5.26 is the answer. Here's the slide that will show you in your PDF that same working the same problem. So the next concept that we're going to look at is flow and velocity in water mains. Okay. All right, our little visual there. So flow is denoted by Q, and that's equal to the area times the velocity. So the area being the surface area, the cross-sectional area of the pipe, velocity being the water flow in feet per second through that pipe. And then flow is, the amount that goes in, say, per second, and the cubic feet per second. So flow is equal to A times V, area times velocity, and the answer will quite often be in cubic feet per second. All right. So water is moving through a 6-inch wide pipe at a velocity of 2 feet per second. What is the flow in CFS? So the first thing we want to do is we need to get the inches into feet. So we're going to divide our 6-inch diameter pipe by 12, and that gives us a half a foot of diameter. Now we calculate the area. So we're going to look at that 0.785 times the half a foot times the half a foot, and that gives us 0.19625 square feet. And finally, we're going to take and use the flow formula, and we're going to multiply the area that we had by the velocity that they gave us, the area we calculated by the velocity they gave us, and that 1.19625 square feet times 2 feet per second is going to give us an answer in cubic feet per second of 0.3925. All right, so one of the things that we're going to end up doing probably when we do problems like this is we're going to be converting back and forth between CFS, cubic feet per second, and gallons per minute. When we go from cubic feet per second to gallons per minute, as you can imagine, we've got, we're going from seconds to minutes. So, our flow in gallons is going to be over a longer amount of time. So we're going to multiply that. In this case, we're going to multiply CFS by 60 seconds per minute, and then we need to convert from gallons to cubic feet, or 2 gallons from cubic feet. Now, when we look at gallons per minute to CFS, we're going to take our flow in gallons per minute, we're going to divide by 60 seconds per minute and multiply by 7.48 gallons per cubic feet to get rid of the gallons and get our answer in cubic feet. So it's also, because it's in seconds, it's over a shorter amount of time. So just important things to keep in mind. So if you've got a pipe that has a flow of a half a CFS, half a cubic feet per second, what's the flow in gallons per minute? So we take our half a CFS, 0.5 CFS, we multiply by 60 seconds in a minute. So that's going to get rid of our seconds. It's going to give us an answer in minutes per minute. And then we multiply by 7.48 gallons per cubic feet so that we can get it from cubic feet to gallons. If we do that calculation, we should get 224.4 gallons per minute. So that's the equivalent of a half a cubic foot per second. Now we're going to go in the other direction. We're going to take a pipe that's got a flow of 500 gallons a minute. What is the flow in CFS? So we take our 500 gallons per minute, and we're going to divide by 60 seconds in a minute. So that gets rid of our minutes and gets us in seconds. And then we need to multiply or also divide the 500 gallons per minute by 7.48 gallons per cubic feet. The gallons are going to cancel, and the cubic feet will come onto the top. So we're going to cancel gallons, we're going to cancel minutes, and we're going to be left with 1.11 cubic feet per second. All right. So we'll do a practice problem of this nature. And in that practice problem, we've got a 500-foot section of 6-inch water main that needs to be flushed at a velocity of 5 feet per second. So this is something that this type of thing is something that maybe you need to do if you've had a main break, you're installing a new water main, concerns about, maybe you're flushing hydrants and that's your goal. So that's why you might need to do a problem like this. So what's the minimum flow required in GPM? All right, so we're gonna we need to find that flow that's necessary to attain our required velocity. So we're going to use the area times velocity is equal to flow. Q equals AV. So first thing is we don't know what the area is, so we need to calculate that. Once again, we take our area is equal to 0.785 times the diameter times the diameter. In this case, the diameter is 0.5. And that gives us an area, cross-sectional area of 0.19625 square feet. So we've got part of what we need. So next, we need to take and use that flow is equal to area times velocity. And if we do that, we've got our area is 0.19625 square feet. We know that our velocity that we were given is 5 feet per second. So we'll end up with something in cubic feet per second, and that is 0.98125 cubic feet per second. But we need to convert that from cubic feet per second to gallons per minute. So we take our number in cubic feet per second. We multiply that by 60 seconds in a minute to get rid of the seconds. We multiply that by 7.48 gallons per cubic feet to get rid of the cubic feet and to get our answer in gallons. And our answer should be in gallons per minute because that's our units that are remaining. And it comes out to 440.4 gallons per minute. And in that case, to obtain that desired flow, we may have to do things like opening or closing hydrants in order to achieve the flow that we're hoping to get. So here we've got a stream flowing into a reservoir. It's estimated to flow at 2.5 cubic feet per second. What would be the estimated flow in gallons per minute? We take our 2.5 cubic feet per second. We multiply by 7.48 gallons per cubic feet. So that we're getting rid of our cubic feet, leaving us with gallons. And then we multiply by 60 seconds per minute because we need to get rid of our seconds and get it into per minute. So we do that, we multiply that out, and we get 1,122 gallons per minute. So now we're going to go back to our weir overflow rate, but we're going to look at a rectangular basin. So in this example, we've got a rectangular sedimentation basin. It's got 4 weirs, each one's measuring 50 feet, and it receives a flow of 3.9 cubic feet per second. So we want to know what the weir overflow rate is for the basin. So the first thing that we're going to need to do is we're going to need to convert our flow to gallons per day. And we can do that. We can take our 3.9 cubic feet per second, multiply by 60 seconds per minute, multiply by the number of minutes in a day. So that's going to convert from cubic feet per second to cubic feet per day. And then we're going to take and multiply by 7.48 gallons per cubic feet to get us into gallons and out of cubic feet. So we do that long. We multiply those out and we get 2,520,461 gallons per day. All right. So now we need to know what the total length of our weirs are. So we have 4 weirs and they're each 50 feet long. So if we multiply that out, we get 200 feet of weirs. That's our weir length. Now we're going to divide our flow of 2 million to just over 2.5 million by our weir length of 200 feet. And that gives us 12,602.3 gallons per day per foot. All right. So now we're going to go back, and our next poll is here. We're going to look at water main again. And we've got an 8-inch water main. It's being flushed with a flow of 720 gallons per minute. What is the water velocity in the pipe? Okay, so we're gonna end the poll, and I will go over the problem. So, all right, thank you, Ingrid. So we've got an 8-inch water main. It's being flushed with a flow of 720 gallons per minute. What is the water velocity in the pipe? So there's a couple things we have to do. First of all, we want to convert from 8-inch to the equivalent in feet. So we take our 8-inch, we divide it by our 12 inches in a foot, and that gives us 0.67 feet. We're also going to need to determine the area because our flow equation requires either we have, in this case, we need to have our area and our flow in order to get our velocity. So we're going to take and do a conversion. We'll take our 720 gallons per minute. We're going to multiply that by 1 minute for 60 seconds. And then 1 cubic foot per 7.48 gallons. So our gallons cancel, our minutes cancel, and we're left with something in CFS per second. And that is CF per second, or cubic feet per second. It's 1.6 CFS. All right, so that's our flow. We need our pipe area. Pipe area is going to be equal to 0.785 times that 0.67 times 0.67, which is going to give us 0.35 square feet. Now, Q is equal to A times V. We know Q, that's 1.6 cubic feet per second. Oop, thank you. And we know our velocity, or we know our flow, or our area, excuse me, I'll get the right term eventually, is 0.35 square feet. And we just don't know our velocity. So if we take and divide each side of our equation by 0.35, so we get 1.6 feet per second divided by 0.35 square feet. It'll cancel out here, and that's going to give us our velocity. If we do that, V is equal to, I'm showing you enough room, give enough room, 4.57 feet per second. Okay. All right. And I'll share the results. We have 59% said 4.57. We've got 18% at 1.6, 12% at 0.35, and 12% at 0.67. The last two being potential, that's part of the work. So those are a little bit tricky. We give you an answer that's only that you need to find, but it's not the ultimate answer in the end. So 4.57. Here's the solution for the slides. So our next concept we're going to talk about is pressure and head. That'll take us a good deal of the way through the remainder of today's training. And so pressure is the force applied to an area, and we express it typically in pounds per square inch. Whereas head is the height of a water column that is exerting pressure, and head is expressed in feet. So we have there are some relationships that we have between pressure and head. So 1 psi is equal to 0.433 psi per foot times the height in feet. So that being said, 1 psi is equal to the height in feet divided by 2.31. These numbers are reciprocal. So the idea is that if you were to take 1 and divide it by 2.31, you're going to get 0.43. And if you could take 1 and you divide it by 0.433, you're going to get 2.31. So we can utilize these. If you're doing one of these problems, it's another thing where you can use one or the other. If you know one, you don't necessarily have to know the other. And pressure, we can look at pressure as a function of weight and area. So if we look at a cubic foot of water in the shape of a cube, went through this previously. The weight of a cubic foot of water is approximately 62.4 pounds. And why is that such? Because we know that a cubic foot times 7.48 gallons per cubic foot times 8.34 pounds per gallon is equal to 62.4 pounds. So our gallons cancel, our cubic feet cancel, and we're just left with an answer in pounds. But how much force does the cube of water exert due to its weight? So in this case, since the bottom of the area of the cube is a square foot, and because the cube weighs 62.4 pounds, we can include that the force is equal to 62.4 pounds per square foot. The force per square inch, we can calculate that, and we can just take our 62.4 pounds, divide that by 144 square inches. You guys are welcome to do this on your calculators. But lo and behold, it comes out to 0.433 psi. So this whole thing just kind of comes around. Does this number look familiar? It's the static pressure exerted by a water column that is 1 foot high. So it's just 1 foot of water is equal to 0.433 psi. So let's look at a practice problem. In this example, we've got we want to determine the pressure exerted at the bottom of a cylindrical water column with a diameter of 6 inches and a height of 5.1 feet. First thing that we want to do is we want to calculate the volume in cubic feet. We've done that many times today. We take that 0.785 multiplied by the diameter times the diameter and times the height, in this case of 5.1. And that tells us that that's 1 cubic foot. Now we want to determine the weight of the water. We take our 1 cubic foot. We're going to multiply that by 7.48 gallons per cubic feet times 8.34 pounds per gallon, and we get our 62.38 or 62.4 pounds. The next step is to determine the bottom area in square inches. So if we take, and we can go back to inches in this case, and we can take and multiply 0.785 times the diameter of 6 inches times the diameter of 6 inches. And that tells us we have 28.26 square inches. That's the area of the bottom of our column. And then we can determine our force in the force per square inch. So we take our weight of water of 62.4 pounds, we divide it by 28.3, get 2.2 pounds per square inch. And in this case, that's a different pressure from our cube because the height's different. So the height is important for pressure. All right, so if we go back to if we take 0.433 psi per foot, and we multiply it by our height of 5.1 feet, we get 2.2 pounds per square inch. Now, if we take and go back, we take our 5.1 feet, and we multiply that by 1 psi per 2.31 feet, lo and behold, we get that same answer. So as I said, it doesn't matter which one of those, whether you use 2.31 feet per psi or if you use 0.433 psi per foot, we can just flip those fractions up and down and we can multiply them and use them. And you really only need to memorize one to make these problems work. So we're on to our poll 15. We've got the question is, what is the pressure at the bottom of a standpipe filled to the 40-foot level? Okay, we will close the poll and I will work the problem. All right, so what is the pressure at the bottom of a standpipe with a diameter of 12 feet filled to the 40-foot level? So the pressure, P, is going to be equal to the 40 feet of water. And we can do it I'll do it both ways. And we're going to multiply that by 1 PSI per 2.31 feet. The units will cancel out. We get an answer of 17.3 PSI. And the other way to do this would be to take our 40 feet of water. We're going to multiply that by 0.433 PSI for 1 foot. Our feet cancel out, and we're left with an answer in PSI, and that's 17.3 PSI. So this is what I mean by we can, remember one or the other of these. You don't have to remember both in order to do these problems. We can always just use the one we need or that we remember. So in this case, we're looking at every 2.31 feet of water column adds 1 PSI to our total. And then in this case, we're looking at every foot of water adds 0.433 PSI of static pressure. Okay. I'll share the results here. So it looks like 80% also had 7.3. All right. So the 7.3 is the correct answer. Here's the slide that shows that for the PDF that you guys received. So one of the things that can help people when they look at this idea of pressure is the idea that we have cubes of water that are stacked one on top of the other. All right. I don't know how, hopefully that came across okay to you guys. Each cube weighs 62.4 pounds. We've talked about that. And it exerts a pressure on a 1 square foot area. So if we've got a water height of 6 feet, what do you think the pressure is going to be? Well, it's taking that 6 feet times the 62.4 pounds per cubic feet. It gives us 375 pounds per square feet. We can convert that to PSI if we divide it by 144 square inches. When we do that, we take our 375 pounds per square foot, we multiply by 1 square foot per 144 square inches, and that gives us 2.6 pounds per square inch. So let's look at a real world example. All right, it's a pretty busy slide we've got here. We've got a pressure example for a ground storage tank. And our example is a 10-foot wide by 20-foot long by 6-foot deep tank. It's going to hold 8,967 gallons of water when it's full. The water weighs 74,850 pounds. We figured that out by multiplying 8,976 gallons by the 8.34 pounds per gallon. And it acts on the 10-foot by 20-foot bottom of the tank. What is the pressure in PSI on the bottom of the tank? So the first thing we're going to do is we're going to calculate the pressure in pounds per square foot. So we know there's 6 foot, it's 6 foot high or deep. The tank is 6 foot deep. There's 6 foot of water in there. We're going to multiply that by the pounds of water per cubic feet. We know that's 62.4 pounds per cubic feet. So we're going to get rid of the feet there. We get that down to 2, and we end up with an answer of 374.4 pounds per square feet. That's the pressure in pounds per square feet. Now we need to convert that to PSI. So in order to do that, we know that there's in 1 square foot, that's 12 inches by 12 inches. That's 144 square inch that we talked about before. The pressure in PSI is going to be, we take our 374.4 pounds, per square foot, we multiply by 1 square foot per 144 square inches. That gets rid of our square feet, and that gives us an answer in pounds per square inch, or PSI, of 2.6. And one thing to note is that the pressure is the same as the previous cube example. So the amount of, the fact that we had, 74,850 pounds total of water doesn't affect what the PSI is. It's that column of water on it, how high the water is, that's important when it comes to that. All right, so move on to a practice problem we have here. We've got a 100-foot high elevated tank, and it sits on top of a 35-foot high hill. What is the water level in the tank? The water level in the tank is 11 feet below the tank's top. There's a hydrant at the base of the hill. What is the water pressure as the hydrant nozzle if the nozzle is 2 feet above the ground? So we're going to assume static conditions, no flow, no head loss, anything like that. So the first thing that we need to do is we need to calculate the feet of head. All right. So we take the 100 feet that we have. Now it's 11 feet down, so we have to subtract that 11 feet off. We're going to add 35 feet because that's the distance between the base of the tank to the top of the hydrant, or excuse me, to the base of the hydrant. Base of the tank, base of the hydrant's 35 feet, but the nozzle's 2 feet up. So we add the 35 feet, we subtract the 2 feet. When it's all said and done, we're going to have 122 foot of head from the water in the water tower tank to the nozzle on the hydrant. Now we can calculate the pressure in PSI. You can use whichever of those formulas or whichever one of those conversion factors you like. In this example, we're using 0.433 PSI per foot. You could use a 1 PSI per 2.31 feet if you like. Either way, we'll get 52.8 PSI. And then the other way to do it, we take the 122 feet, divide by 2.31 feet per PSI, and lo and behold, we get the same answer. All right. So head and elevation lift, water pressure can lift water. So we can move water, we can lift it through pressure. The height that water can be lifted with a given pressure is what we call head. We consider a water main that's pressurized to 60 psi. What is the maximum theoretical height that water could be lifted? All right. So we're going to convert from psi to feet. Right. So we take our 60 psi, we multiply that by 2.31 feet per psi. And that gives us 138.6 feet. So once again, you could have used 0.43, 1 foot over 0.433 psi. You would get the same answer. But one thing to note with this is that at that 138.6, if I could reach it, at that level, there's going to be no pressure. I mean, the water could be pushed up that point, but at that point, if you were to check it, there's no more pressure there. In reality, you're going to have some losses. It won't quite go that high because we've got things like pipe friction and stuff that's going to affect that. So it would be slightly less than that. Water service connections need to meet a minimum standard of 35 to 40 psi. Typically, you would want to see a minimum of 20 psi in emergency conditions. And I'd say that like the American Water Works Association recommends 40 to 80 psi for normal conditions. All right, so let's look again at we're going to talk about a service connection. We've got a water main pressure to 60 psi, supplies a house connection that is 50 feet above the main. What's the pressure at the house service connection? We're going to disregard any friction losses, purely just the simple numbers. So we take our 60 psi, we multiply by 2.31 feet per psi. we do that, our PSI goes away, we'll end up with a number in feet, which is 138.6 feet. We subtract the elevation to determine the remaining head. So we had 138.6. We subtract the elevation of 50 feet, which tells us that we have 88.6 feet of head remaining. Now we use one of our conversion factors, convert that back to PSI. In this case, it's 38.4 PSI, which is sufficient. All right. So our next one is a pole. We're taking kind of these same concepts. We've got an elevated storage tank that's filled to the 20-foot level. The bottom of the tank is 110 feet above a 6-inch water main. What is the static pressure at the house connection that is 35 feet above the water main? Keep in mind, we've got to do that adding and subtracting. We got to make sure that that we're starting with the right amount of head. I'm going to end the poll and I will go through the problem. All right, so we've got an elevated storage tank. It's filled to the 20-foot level. The bottom of the tank is 110 feet above a 6-inch water main. What is the static pressure at a house connection that is 35 feet above the water main? Okay, so the first thing was we need to determine the head at the service connection. So we're going to take the 20 feet that we have of water in the tank. We're going to add that to the 110 feet that we have from the base of the tank or the bowl of the tank to the water main. And then we need to subtract off the 35 feet that it is up the hill from the water main to the house. And that's going to give us 95 feet. Okay. So we take our 95 feet and we're going to multiply that by, once again, you can use whichever of these you like. 1 psi per 2.31 feet gives us 41.1 psi. Obviously, we could do 95 feet times 0.433 psi per 1 foot, and we would get the same answer. Okay, so let's look at that in comparison to the polls, or the poll. Share the results. 80% of the people said 41.1 psi. And we also had a few 95.3s and a 71.4. All right, good work. All right, so next topic we have is horsepower. All right, so this can be important if we're for the water industry, and we horsepower is the head and flow are used to calculate horsepower in a water system. So we use both the head and the flow to calculate that horsepower. So we've got a formula for that, and it's the flow in gallons per minute times the head in feet divided by 3,960. Okay, so I bet we're kind of wondering, where's this 300 or 3,960 come from? So a horsepower is the power required to lift a weight of 33,000 pounds, a vertical distance of 1 foot in 1 minute. Okay. So if we take 33,000 pounds, we divide that by 8.34 pounds per gallon, that gives us 3,960 gallons. Sorry, a little behind on my clicking. 33,000 pounds divided by 8.34 pounds per gallon gives us 3,960. So for an example, we've got water being pumped at a flow of 500 gallons per minute and a head of 138.6 feet or 60 psi. What is the water horsepower? So we take our 500 gallons per minute, that's our flow, multiply by 138.6, that's our head. We divide by the 3,960, and that gives us 17.5 horsepower. That's the amount of power transferred to the water in the form of flow and pressure. The motor and pump horsepower needs to be a little higher to accomplish that, because we've got things like friction and efficiency losses that are going to diminish that. So you'd want to, that would be, it would need to be more than 17.5 horsepower. All right, chemical dosage and feed. So our next topic. Some of the things that when we talk about chemical dosage and feed, we want to look at our concentrations. There's several different ways to express concentration. We've talked about percent, that's parts per 100. Decimal equivalent of 1% is at 0.01. Parts per million is 1 part per a million parts. And when we're looking at concentrations, milligrams per liter and parts per million are the same thing. That's kind of can be a difficult concept, but when we talk about milligrams per liter, we're talking about the weight of solids. So that would be our milligrams that are in a 1 liter sample. So it's weight per volume. But because a liter of water weighs 1,000,000 milligrams, we can use it as a concentration. And then if you were wondering, like, how many parts per million is equal to 1%, or how many milligrams per liter is equal to 1%, that's 10,000. You'll hear me quite often, things will be written as milligrams per liter, and I'll call them as parts per million, just kind of enforcing the fact that it's the same thing. So if we want to calculate feed rates, we're going to have to we need to determine the number of pounds per day of something that we're feeding. We're going to take our flow in million gallons per day. We're going to multiply that by our dosage, which is milligrams per liter or parts per million, times the weight of water, a gallon of water, which is 8.34 pounds per gallon, and that'll give us pounds per day. It's the pounds formula. Okay. We use it for chemical feeds, dosages. And once again, we're reinforcing the fact that milligrams per liter is the same as parts per million. So the formula works for any chemical, but the chemical has to be 100% pure, which doesn't happen very often. It does in the case of gas chlorine. Gas chlorine is, or chlorine gas, is 100% pure chlorine. So that's kind of the base example that we're going to use. So we've got a water system that's got a flow of 2 million gallons a day. It needs to be disinfected with a dose of 2.1 parts per million chlorine gas. What would be the feed rate of chlorine gas in pounds per day? So we're going to take and use our pounds formula, which is flow in million gallons a day times the dosage times 8.34 pounds per gallon, and that'll give us our pounds per day. So we plug in our numbers. We've got 2 million gallons a day, and we'll multiply that by 2.1 parts per million times 8.34 pounds per gallon, and that gives us 35.03 pounds per day. And so when you get that, you would adjust your chlorine gas feed so that it's 35 pounds per day, but then you're going to have to check your residuals to see where you're actually, because when you apply chlorine, some of that's going to be taken up, it's going to be used up. And so 35 pounds per day is not necessarily going to get you exactly to 2.1, but it's a start. And from there, you would just move up to the point where you got to your 2.1 parts per million. I wanted to make a note earlier. We would have had the schedule for a 15-minute break. My intent is just to continue through. We'll get through this. Hopefully we'll be done early. There may be an opportunity. I have some extra problems that I could work if that's what people would like to do. So we're just going to power through, and those who want to leave will have the opportunity to get done a little early. Just some informational stuff about gas chlorine and setting a feed rate. So this is kind of a gas chlorine setup. We've got our canister, and there's liquid gas, and then the chlorine gas comes off. It goes through regulator. There's a rotometer. It reads in pounds per day, so we can set that. It'll tell us how many pounds per day, and we can adjust for that. And that ball floats as the gas goes through, and that tells us how much is going through. And then we adjust it by the regulator needle valve. You can see down here that we've got a vacuum is created by this venturi. When it goes from big to small to big, we get a venturi there. And that pulls it causes a suction, and it pulls the gas into our feed line. All right. So pounds formula can be rearranged to solve for a dose. So much like we've done with our other equations. We can move things around to because we're not always going to be looking for pounds per day. We may want to determine the dose. We don't want to determine the flow. So we can adjust our formulas to do that. So in this case, we want to arrange it for dose. So we would take and divide each side of the equation by our flow and 8.34 pounds per gallon. So that's our original equation. If we divide both sides of the equation by flow times 8.34, that's what it would look like. And we can see how it cancels out. So what we end up with on the right-hand side is just the dose in milligrams per liter or parts per million. On the left-hand side, we have pounds per day divided by the flow in million gallons a day and by 8.34 pounds per gallon. So that probably is easier to look at if we were to rearrange it so that we have the dose is equal to pounds per day divided by flow in 8.34. So in our practice problem, we've got an operator that checks the settings at a treatment plant. The operator notes that the gas chlorine feed rate is set at 30 pounds per day and the plant flow is 2.1 million gallons a day. He wants to know what the dose is of chlorine in parts per million that it's being administered. So we take our dose formula from our pounds formula, and we can put the information in. We know the pounds per day, that's 30 pounds per day, and we know the flow is 2.1 mgd. So we simply put those numbers into the formula, and that's our dose is equal to 30 pounds per day feed divided by 2.1 million gallons a day times 8.34 pounds per gallon. And that gives us a dose of 1.71 parts per million. Okay, so now we have our next pole. And as you can imagine, it's going to be something to do with pounds formula. So a well produces a flow of 600 gallons per minute and a chlorine dose of 1.5 parts per million. What is the feed rate for gas chlorine in pounds per day? Thank you, Scott. Okay, so we're going to end this poll and I will go through the solution. All right, so we've got a well that produces a flow of 600 gallons per minute and a chlorine dose of 1.5 parts per million. What is the feed rate for gas chlorine in pounds per day? So the first thing we want to do is convert the flow to million gallons a day. So if we take our 600 gallons per minute, and then we're going to multiply that by the number of minutes in a day, 1,440 minutes. I like to put it below. So our minutes are going to cancel out. And that gives us 0.864 million gallons per day. All right. We got to divide that. If we divide this whole thing by a million. So now if we take our 0.864 mgd times 1.5 parts per million times 8.34 pounds per gallon, we get 10.8 pounds per day. Okay. So we'll share the results here. It looks like 63% of the responses are 10.8 pounds per day, and we had 37% at 7.5 pounds per day. Okay. Let's see here. 10.8 it is. There's the solution. All right, so now we're going to talk about liquid chlorine or sodium hypochlorite. They're often called bleach. So that's the liquid form of chlorine. And the strength of, we talked about gas chlorine be 100% available. Sodium hypochlorite or liquid chlorine, liquid bleach, whatever you want to call it, is typically in the range of 5.25% to 12.5%. And it's somewhat volatile. That those concentrations will definitely go down throughout time. So that's in part why there's a range. Plus, it is manufactured at different concentrations for different things. Sorry, I was a little behind on my clicking. So in order to utilize liquid chlorine, which is much more commonly used than gas chlorine, we need to modify our formula so that we can take into account the percent strength. We need to calculate the feed rate in gallons per day instead of pounds per day. And we need to account for, as part of those differences, when we've got different concentrations, we're going to have, a different weight per gallon. So our specific gravity, which is a comparison of the weight of something to the weight of water, changes. So 12.5% bleach is typically 1.2 times heavier than water. So if we were to look at that, if the weight of water is 8.34 pounds per gallon and we're 1.2 times heavier, then the weight of liquid chlorine, 12.5%, is typically around 10 pounds per gallon. So if we look at if we're calculating feed rates for sodium hypochlorite, this is our pounds formula. The top of this equation, it calculates the pounds of pure chlorine, and the bottom, we're taking into consideration the strength of the liquid chlorine, and then the weight per gallon. So in our equation for gallons per day is going to get modified to the million gallons a day times the parts, or the dose or parts per million times 8.34 pounds per gallon, divided by the percent strength times the specific gravity times 8.34 pounds per gallon. that specific gravity times 8.34 pounds per gallon is the weight per gallon of the liquid chlorine. All right, so let's move on to a practice problem. Let's put this into motion, what we're talking about. So what is the feed rate for 12.5% sodium hypochlorite with a specific gravity of 1.2 when the plant flow is 0.5 mgd and the dosage is 0.9 parts per million? So we're going to use the gallons per day, our pounds formula here. And we'll plug in those values. Let's see, here we go. So gallons per day is equal to flow in million gallons per day times concentration times the weight of water times divided by the percent strength times the specific gravity times the weight of water. So if we put our numbers in, we've got a flow of 0.5 million gallons a day. We've got a dose of 0.9 parts per million. And there's our constant of 8.34. We know that it's 12.5%. So 12.5% is equal to 0.125. And then we multiply by the specific gravity, which we were told is 1.2, and then divided by that, or also divided by the constant of 8.34 pounds per gallon. So if we do that, we end up with 3 gallons per day. And as I pointed out, the percent strength, we're going to convert from 12.5 to a decimal, and that conversion takes it to 0.125. All right, so now we're on to poll number 18. So on poll number 18, we've got a groundwater well that produces a flow of 850 gallons per minute. The chlorine dose is 1.3 parts per million. What is the feed rate in gallons per day for 12.5% chlorine with a specific gravity of 1.2? All right, thank you, Scott. All right. We've got 80, 85% participated. All right. So we're gonna end the poll. And I will work the problem. All right. So got a slide. There we go. Oh. So we've got a groundwater well producing a flow of 850 gallons per minute. Chlorine dosage we're looking for is 1.3 parts per million. We want to know what the feed rate in gallons per day is, utilizing 12.5% liquid chlorine with a specific gravity of 1.2. So there's a couple things we need to do here, but the first thing is to convert our flow from gallons per minute into million gallons a day. So if we take our 850 gallons per minute, we're going to multiply that by 1,440 minutes per day. So that'll give us in gallons per day. And then if we want to convert into MGD, we're going to multiply that by a million gallon per million. That's a one with 6 zeros after it. Gallon. So their gallons cancel out. We're left with million gallons per day, and that's 1.22 MGD. Everybody can see that. All right. So then we want to use that the formula that we had for liquid chlorine, where we take the flow in million gallons per day. That's 1.22. We multiply it by the dose of 1.3 parts per million. We multiply that by 8.34 pounds per day. We divide the whole thing by 0.125. Slide up. Okay. So that's the concentration converting from 12.5% into a decimal form. And then we multiply that by the specific gravity of 1.2. And then we multiply by 8.34 pounds per gallon. Okay. So this should be pounds per gallon. So as you can see, these pretty much cancel out. We do our calculations and we should get somewhere in the ballpark of 10.57 gallons per day or 10.6, somewhere in that range. Okay, so then we would, after we figure this out, we would then set our meter to put an output of that. Obviously, we're probably going to need to dose it a little bit higher for some of the chlorine that's going to get used up by the things in the water. And then the other thing is that usually chemical feed pumps are rated in gallons per hour. So we may need to make a conversion to gallons per hour. And to do that, we would take the gallons, the 10.57 gallons per day, multiply it by 1 day for 24 hours. That's roughly 0.44 gallons per hour, which would probably be a little more compatible with our feed pump. Okay, so we want to show the results. And 70% said 10.57 gallons per day. We also had a few answers for the others at 70% for 12.68 and on down. Okay. All right. And here is the solution that would be in your packet. So we're pretty much to the end here. And what did we cover today? fractions and conversions, areas and volume, filtration rates, sedimentation basin loading. We did some stuff with velocity and flow rates, head pressure, horsepower, and then finally we ended with dosage and chemical feed. As you can see, Scott put in the chat about the attendance self-certification and course evaluation survey is on that SurveyMonkey link. Please fill that out. We need that information in order, especially for those who are hoping to get CECs. This is approved for CECs for drinking water for both the states of Indiana and Michigan. And then they say there's three things, hopefully, that you can learn from a training like this. And so, we're hoping that you learn the concepts of flow, whether it's in the different units, gallons per minute, gallons per day, million gallons a day, CFS, and how to move back and forth between those units. Head and pressure, that idea that whether it's 1 psi per 2.31 feet, or if it's 0.433 psi per 1 foot. Hopefully you remember some of those concepts. And then your chemical feed dosage, the pounds formula, the flow in the right units, million gallons a day, dosages in parts per million, stuff like that. So yeah, and we appreciate that that you attended today. I hopefully you learned something useful to you. And when you're filling out the survey, please let us know. This training, as I had said, was originally planned to be an in-person training, and then we extended it to a hybrid where it was going to be in-person and virtual. And then we didn't get in-person, people signing up, so it went just virtual. So I don't know if you noticed, compared to maybe some of our other trainings, there were probably more poll questions and more working problems, and I think that was in part because of the intent for it to be an in-person training. So yeah, let us know what you think of the format. I know that for some it may have been too slow, some too quick, not too much, too little. All that stuff is helpful, and us planning out future trainings. So that being said, we are happy to answer any questions. I do have a few extra questions or problems that I've worked up. If there's something that in particular that maybe you would like to see done again, I can see if I can find a problem that's similar.
Thanks for attending today's session. The SurveyMonkey link is in the chat. That is how you will record your attendance for today's session through the self-certification and course evaluation survey. Once you fill that out, it should take you to the end, and I believe it's a splash page on the SurveyMonkey site that says, thank you for completing the survey. You won't get anything immediately. It takes a little bit of time to process the certificates of attendance for today's session. But once you've filled out that link, you're free to go. Thanks for attending today's session, and we hope to see you again in the future.